In Module 18C, we want to do a brief review of acid-base titrations, working on writing net ionic equations for any acid-base titration, and determining the concentration or volume of titrant required to reach the equivalence point in a titration. After this, I've got 2 more modules that are pretty long, doing calculations of pH at different points within a titration curve. I have these split up because even the way they're split up, they can get pretty long. I cannot put all this together. So this part should be a review from first semester. If you're comfortable with it, go ahead and skip to the next part. But if you're not comfortable with this, if you're not quite real clear on what we mean by titration from first semester, go ahead and watch this. It shouldn't be too bad. Or it should be a nice review. It should come back pretty quickly. If it doesn't come back pretty quickly, you need to review in Chem 1. So what is an acid-base titration? An acid-base titration is a neutralization reaction. It's an acid plus a base that gives you a salt plus water. Generally speaking, either the acid or base is a standardized solution, meaning that you know the concentration of that solution. A standardized solution has a known concentration. The known concentration can be then used to determine the concentration of another solution. We see here some different examples of titration. So we've got here in your Erlenmeyer flask an acid, adding base to it. So acid plus base, we're going to have salt plus water. We start adding base, and as we're adding base, the base starts finding these OH minus starts finding the H plus ions, and they react and form water. The salt that's formed is your spectators or your conjugate acids bases. We're not worried about that right this second. That we're going to worry about in the next module when we talk about pH changes. But it's going to start neutralizing each other and creating your salt plus your water. Eventually, we reach your equivalence point, and your equivalence point is when all of the H plus has been used up, and we now have equal molar ratios. So the number of moles of H plus equal the number of moles of OH minus in solution. What we see here in color is a titration with an indicator called phenolphthalein. It's a very common indicator that's used because in acidic solution, it is clear, and in basic solution, it's pink. We use this because we're adding base to it, so it should be clear when we have an acid, and eventually once we hit our equivalence point, and then past our equivalence point, we reach what we call our endpoint. Endpoint is past the equivalence point, and it's where we see the solution has turned color and the titration is complete. At least one component in a titration must be a strong electrolyte, because we need something that will dissociate fully to be able to tell when the reaction is complete. So remember, for acid-base titrations, you need to understand net ionic equations. If you have a strong acid plus a strong base, you've got H3O plus OH minus, giving you 2 moles of water. Everything else is a spectator. Remember, net ionics, we leave out spectator ions. If we have a strong acid plus a weak base, your strong acid is H3O plus. Remember, H3O plus on the reactant side means strong acid. Weak base, AQ, or weak base is B, and it's aqueous, giving me HB plus H2O. You can also have a strong acid, weak base system where you have strong acid, H3O plus conjugate base, giving you HA plus H2O. And weak acid, strong base, weak acid, HA plus strong base, OH minus. Remember, OH minus on the reactant side is a strong base. These react to give you your conjugate base plus water, or the other weak acid, HB plus plus your strong base, OH minus, will react to give you your weak base plus water. Now, these are simplified down, yeah, by writing just A minus, HA, B, and HB plus, I've simplified it down. All reactions you look at can be simplified down. These are for monoprotic. You may have diprotic. You need to pay attention if you have HA, H2A, or H3A. You need to know which one you're dealing with because it's a different number of moles of acid to base if you have diprotic and triprotic compared to monoprotic. So a bunch of terms that you need to be familiar with if you are not already. Your titrant. The titrant is a solution of known concentration that's added from the burette to the analyte or unknown in the Erlenmeyer flask. Now, we say known concentration. Every so often you will have a titrant that you are actually standardizing. We will do that in, like in lab, for instance, we standardize a solution of sodium hydroxide. So we standardize it so that we can then determine the concentration. Most often, though, the titrant concentration is known ahead of time. The analyte is what you are titrating. It's your most often your unknown, and it's what you are titrating. Meaning adding to. The titrant is what you're adding from the burette. Burettes are a device used to deliver a specific volume of liquid. And it's a great way for us to know an exact amount that was delivered. Equivalence point and endpoint. These are different things. An equivalence point is the point in the titration when the number of moles of titrant added is chemically equivalent to the number of moles of analyte. The endpoint is the point in the titration where the reaction is assumed to be complete as shown by the indicator. The endpoint often involves a color change and needs to be as close to the equivalence point as possible. Okay, so first, some terminology. We would say we titrate the analyte with titrant. So that's adding the titrant to the analyte. We titrate the analyte with titrant. Equivalence point. What do I mean by chemically equivalent? I mean if I have a weak acid plus a strong base, the mole-to-mole ratio here is 1. Of acid to base. 1 mole of acid to 1 mole of base. This is called monoprotic. If I had H2A plus OH minus, giving me A2 minus, plus H2O, I would see I need a 2 here and a 2 here to balance out the reaction, and 1 mole of H2A requires 2 moles of OH minus. When 1 mole of HA is equal to 1 mole of OH minus, I have reached the equivalence point for a monoprotic. For a diprotic, 1 mole of acid to 2 moles of base. This is when they are chemically equivalent. The number of moles of the analyte equal the number of moles of titrant that has been added. The endpoint is the point just past your equivalence point. It's the point where the color change, we add indicators to solution so that we can visibly see with our eye, oh, the titration is done. The way indicators work is they react with the titrant and turn color, but they react at a slower rate than the analyte we're looking at. So at the end point, all of our analyte is gone, all of the analyte is reacted, Now I add just a little bit more base and it reacts with the indicator. When it reacts with the indicator, it turns the solution color. I now know the titration is complete. I am just past the equivalence point. So, for example, 40 mils of monoprotic acid, monoprotic means HA, is titrated with 0.125 molar NaOH. If 25 mils of base, OH minus, is required to reach the equivalence point, what is the concentration of the acid? I've got acid, I'm adding base, I'm forming conjugate base plus water. I want to know what is the concentration of acid. So number of moles of my acid to liters of my solution. I'm starting with a 0.125 molar solution of base, so 0.125 moles in 1 liter of base. I only use 25 mils of base, so 0.0250 liters of base. So if I had an entire liter, I would have 0.125 moles. I don't have an entire liter. I have 25 mils of it. This factors in that ratio of how much I actually have. It's monoprotic, so I know that 1 mole of acid reacts with 1 mole of base. And I'm told that I use 40 mils of the acid solution. So at this point, I've gotten rid of my moles of base converted to moles of acid. I've gotten rid of liters of base. Now I need liters of acid in here. 0.0400 liters of my acid solution. 0.0781 molar. At my equivalence point, the number of moles of acid is equal to the number of moles of base. At the end point, the number of moles of acid is less than the number of moles of base. Before the equivalence point, the number of moles of acid is greater than the number of moles of base. What can I say about the pH? I can tell you that it depends on what I'm combining here. Before the equivalence point, the number of moles of my weak acid are greater than the number of moles of my strong base. We're going to do the examples in a minute, but what we're going to see is if this is the case, the pH will be less than 7. At the equivalence point, the number of moles of acid equal the number of moles of base. We'll do the math to show you in a sec, but what you need to realize here is that you have neutralized your acid. When this happens, you don't have HA or OH minus. What you really have present is A minus. So the pH will be greater than 7 because you have conjugate base present. These two have neutralized each other. There's not any of them left. Before the equivalence point, if I actually checked it, all the base I've added has gone away, and I only have moles of acid present. At the equivalence point, these are equal to each other. They neutralize each other out, and they form conjugate base. All that's actually present is my conjugate base. I don't have HA or OH minus actually present in solution at that point. The moles have equaled each other. They've neutralized each other out. At the end point, all of this has been used up. I have excess of this and I have excess of this, but the A minus doesn't matter. and the pH will also obviously be greater than 7.